So this next video is going to be still VSEPR examples, but I'm going to do some positively charged molecules just to show you how different those ones are. So the first example is NH4+. So follow all the same steps. So step 1 is to count valence electrons. For nitrogen, I have 5. For 4 hydrogen, I get 4. So I should have 9 valence electrons on this molecule, but it's positively charged. So I have to, don't forget this step. Everybody sometimes forgets this step. So don't forget that a cation has lost electrons, so we have to lose one. So now we only have 8 valence electrons to work with because of the positive charge. If we had a negative charge on the molecule, that would mean it had an extra electron and we would have to add some. So we have 8 valence electrons to work with. Same step 2, you just take your guess. I'm going to put nitrogen in the middle because it's the fewest, and I have 4 hydrogens, and those are probably going to want to go equally as far apart as they could from each other, so I'll put them like 90 degrees. So that's my guess. And then I just want to count up how many electrons I use. So there's 2 in that bond, 4, 6, 8. And when I subtract that from my total, I have 0 electrons left over. So this must be my final guess. So I always say check your formal charges. And it especially is important for molecules that are charged because the rule is the formal charge should equal the charge on the molecule. So because we have a positive charge on this NH4, all of our formal charges have to add up to a total of a +1. So let's make sure that happens. For hydrogen, we'll check that one first. You're going to do, I'll just remind the formula over here. It's the valence electron number, or the group number, minus the number of lone electrons, minus half bonding electrons. So for hydrogen, it's in group 1, or it wants 1 valence electron, has no lone electrons, and for each hydrogen, it shares 2 electrons in the bond, so minus half of 2. That gives us our 0. So nitrogen next. Nitrogen wants 5, has no lone electrons, and half of 2, 4, 6, 8 for that nitrogen. So that leaves us with a +1, which is what we wanted because the molecule should have the overall charge of +1. So our guess is right then, and I'll just draw the final answer over here because you want to try draw it in 3D now. So we know it's a A for 1 nitrogen, 1 central atom, and the X is the number of bonding pairs. So I have 1 bond, 2 bonds, 3, 4 bonding pairs around it, and no lone pairs, so no E's, so you don't even have to write it. So AX4 is tetrahedral with 109.5 degrees. So in 3D, I'll draw that over here. These 2 hydrogens are in the plane of the page, or they're just flat on the page. This hydrogen is coming out at me. This hydrogen is going behind the page, back at me. And you can see that 109 degrees, that's right here, 109.5 right here. Between all of them now. So that's how you do the cation examples. And I'll just do one more example for cations, and that would be H3O+. Oops. H3O+. So step 1, count electrons. We have 3 hydrogens, they're each bringing 1, so that's 3. And I have 1 oxygen, that's group 6. So you would think we have 9 electrons to work with, but this molecule has lost an electron because it has a +1 charge. So we gotta lose that electron. by subtracting it, and that leaves us only with 8. Once we have that done, we can take our guess. Again, because oxygen's a fewer number of atoms in this molecule, I'm going to assume that's in the center, with the 3 hydrogens as far apart from each other as they could get, so it would be like in a triangle. Then I just want to see how many electrons I used. 2, 4, 6. I used 6 electrons to draw that guess. So that means I have 2 valence electrons left to draw, and I have no choice. I can't put them around hydrogens because hydrogen does not like valence electrons, so I have to just throw them on the central atom. When I throw them on the central atom like that, that means my guess is wrong now. The lone pairs are too close to these hydrogens here. So this molecule would actually redraw itself as the lone pairs sitting on top of the oxygen, and the hydrogens are forced down to be closer together, just because the lone pairs need more room. Lone pairs repel stronger to a bonding pair than a bonding pair would repel a bonding pair. That's how VSEPR helps us get the 3D arrangement of that. So the VSEPR notation is A for 1 oxygen center atom. I have 3 X's, or 3 bonding pairs with the 1, 2, 3 hydrogens, and I have 1 E because of that lone pair. So this resembles a 4 bond pair, like a tetrahedral molecule, but I've eliminated 1 bond pair for a lone pair, and now the tetrahedral becomes trigonal pyramidal. And before I forget, we should check formal charges here. So the hydrogen is going to be 1 minus no lone pairs, half bonding pair. So that's our 0. It should be the oxygen then that has the positive charge. So oxygen likes to have 6 minus 1 pair of lone electrons, so that's 2 lone electrons, minus half of 2, 4, 6 bonding electrons. So 2 minus 6 minus 3 leaves us that +1 that we wanted. So that means that this oxygen has a positive charge there. So if I wanted to draw that in 3D for you, I kind of have it already over to the right there, but I'll just redraw it again. If I want to look down on top of it, like if I want to look above, the oxygen would be sitting with 2 lone pairs right on top of its head. The hydrogen would be there, and this is where you would see the pyramid, the triangle shape. There's that triangle shape. And the lone pairs sitting on top, or in 3D, it's like oxygen, lone pairs up there, 1, 2, 3 down there. But all you need to know is trigonal pyramidal, and then those bond angles now are less than 109.5. The reason that is less than is because tetrahedral used to be 109.5 with all of those 4 bonds as far apart from each other as they could get, like this. But when I replace one of those bonds with a lone pair, it moves my lone pairs down closer together at the bottom, and that makes my angle be a little bit tighter, so smaller than 109.5, just because lone pairs want to be as far apart from anything as possible. And that's it for that one.